Hello, welcome back to part B of chapter 8, the quantum mechanical model of the atom. In section B or part B, we will go through section 8.4, the wave nature of matter, section 8.5, quantum mechanics and the atom. This is where we will look at the quantum mechanical model of an atom. And lastly, we're going to talk about the shapes of orbital. Remember in part A, I define an orbital. Okay, I draw the parallel between an orbit and an orbital. We're going to talk about the shapes in 8.6. In part A, we looked at the dual nature of light. That is, light can behave as a particle, where a particle of light is called a photon or quantum. For many photons or quantum, and light can behave also as a wave. It has a wavelength, amplitude, and the frequency. Likewise, in Paul's model of an atom, electron behaved as, we looked at how electron relays photons of characteristic wavelength, which we see, or we saw it with different colors. In 8.4, de Broglie reasoned out that if light behave as matter, and then matter can behave as light. In other words, if light behave as matter, that means a particle, matter is a particle, and then matter can behave as light as well, which means any object, be it even human being walking, be it a truck on interstate, is behaving as a wave. In other words, de Broglie proposed that particles could have wave-like character as well. That means we can calculate the wavelength of any moving object. We call specifically the de Broglie wavelength, okay? He predicted that the wavelength of a particle was inversely proportional to its momentum. And momentum is mass times V. This is called momentum. And it is the product of, it is the mass in kilogram. So you have to change the mass in kilogram times velocity. This is velocity in meters per second. So the speed has to be in meters per second. It cannot be miles per hour. If you are given another speed or velocity of any object or any particle in this case, you need to change the velocity to meters per second. So that this is what constitute what we call the momentum. Gonna talk about momentum later. This is called the de Broglie wavelength. Remember, there are so far in part A, wavelength of an electromagnetic wave is obtained using this equation. You know what that means. But in 8.4, this lambda is different from this lambda. This is called de Broglie wavelength, and the question will be specific, that calculate the de Broglie wavelength of XYZ. So you know what that means. You see this? You know what that means. It is called de Broglie wavelength. So if I have lambda equals to Planck's constant of mv, this is momentum. This is momentum. And this is the Planck's constant, which is the same value or the same constant we looked before. It has a numerical value 6.6, 26 times 10 raised to negative 34 joules times seconds, 34. So 6.6 26 times 10 to negative 34 joules time a second. This is Planck's constant. You plug in, you know the momentum, all right, Planck's constant, velocity and mass, you can calculate what we call the Broglie wavelength. This is just, illustration of behavior of matter. Someone was just doing that, or which de Broglie theorized that if light can have material properties, right, matter should also exhibit properties which we have shown, or we can calculate the de Broglie wavelength. It demonstrated that the relationship between mass, and remember mass has to be in kilogram, and the wavelength, we call this de Broglie wavelength. Here is an example on de Broglie wavelength. The question will be specific. It will be categorical in stating that what is the de Broglie wavelength? What is the wavelength of an electron moving? This is a de Broglie because an electron is matter. In this case, it's not electromagnetic radiation such as yellow light or red light and so forth. This is matter, and we're going to calculate the de Broglie wavelength. We don't have to worry about the mass. It's given in meters per second. If it was something else, we'll have to change. You may need to refer to the mass of an electron. It is given at the back of the text, or if not, you need to look at it. It's got to be in kilogram. That's the mass for momentum. So if we want to calculate the de Broglie wavelength with the Planck constant, I'll give you in the exam, you'll be given in the quiz as well, this constant. And plugging in the equation, we should be able to get the de Broglie wavelength of an electron. If you look at how this has been plugged in, this is the Planck's constant. The unit here, this is from what we looked earlier on, that in energy, 1 joule equals to kilogram times mass meter per second. Mass in kilogram meter per second. If a conversion factor, we'll have to cancel out the unit, reconciling that so that the unit cancel out in terms of joules and joules. And then 1 second here, we'll go with 1 second, and then the other second will. Now, this can be, or you'll end up with wavelength in meters per wavelength in meters, 1.22 times 10 to negative 10 in meters, or you can change to nanometers. In case you're wondering how this sounds, it's because of the conversion factor. So if I want to change 1.22 times 10 raised to negative 10 meters, remember 1 meter equals to 1 times 10 raised to 9 nanometers, or 1 nanometer equals 1 times 10 raised to negative 9 meters. So if I want to get rid of meters, I'm just going to put here 1 meter, 1 times 10 raised to negative 9 nano. 1 meter times 10 raised to negative 9 nanometers. This is not negative, but this is positive 9. This is positive 9 nanometers. Meters and meters will go away. We have 1.2 times 10 raised to 1 nanometer, or 0.122 nanometers. If you're wondering about that, and I gave you earlier on angstrom here. Angstrom, 1 angstrom, all right, equals to 1 times 10 raised to negative 10 meters, or 1 times 10 raised to negative 8 centimeters. Just to give you some of the conversion factors you may need, but just to, in case you are wondering, why do I have all these numbers? This is just the same as if you plug in or key in on your calculator, this is what you will get, but changing to nanometers or changing to angstrom using the appropriate. Will you be given this? You may need to recall, or, when you're doing the homework, change the units. So back to de Broglie wavelength, remember to change the mass to kilogram. If it's in other units, you need to plug in that, and then the velocity has to be in meters per second. Planck constant will be given for that. Those are how you calculate the de Broglie wavelength. One more example on calculating the de Broglie wavelength here. As I said, you will be given, or the question will be specific, will be categorical in asking you what is the de Broglie wavelength of object APC. In this case, this is the mass of our object, so we need to change that to kilogram. Of course, 5.0, not 25, not 20, not 5, but 25 grams times 0.025 kg. This is the mass of the object, and this is mass. Excuse me. Velocity, which is the speed, velocity is in meters per second. So I don't have to worry about that. So therefore, lambda equals Planck constant over mass times the velocity. Avogadro's, I mean the Planck's constant, not Avogadro, but Planck constant 6.626 times 10 raised to negative 34 joules times seconds over mass in kilogram is 0.025 kg times the speed, it's in 5 meters per second, but we need to change the units. Remember kg. This is the conversion factor. This is meter square. This is meter square per second square, so that if you reconcile, 1 second will go with the second there. The remaining second will go with the second right there. Kilogram will go with the kilogram. Meter will go with 1 meter there. Will remain with meter, and joules will go. So at the end, will remain with the distance in. Yeah. So this writing out, check on your calculator. You should have 5.3 times 10 raised to negative 33 meters. If you are asked to calculate in nanometers, and then you, of course, change that using the appropriate conversion factor, and the correct answer here is B. So remember to change the mass to kilogram and speed to meters per second. This is the constant you will be given for Planck constant will be given. You need B for de Broglie wavelength. Changing gears, shifting gears, let's look at complementary properties. Complementary properties are two properties which the more you know they are done, the less you know they are around. Okay, so if I have two objects right here, which are complementary, all right, The more I know more about it, the more I compromise knowing more about B via A and B. Those are said to be complementary. In this case, the speed and the position of an electron, in case you're wondering where it is complementary, is taking us to is we are getting into the atom and looking at the electron, and it happens that the position of an electron in an atom and the speed or velocity at which it is moving around the nucleus are said to be complementary. Speed and the position are said to be complementary. The more we know the other one, the less we know about the other one. They are said to be complementary. In this case, electron has complementary properties. What are those properties? The velocity of an electron moving around the nucleus and the position. The more we know the other one, the less we know the other one. So this is where Eisenberg uncertainty principle, this is the name of a person who came up with a principle regarding the complementary properties of an electron, that there is uncertainty in position, uncertainty in velocity. There is no way we can know that. Mass, all right, this is the mass and got to be mass in kilogram. So if we have that, this is called Eisenberg uncertainty principle. This is uncertainty in position. This is uncertainty in velocity. Velocity is a speed, the same thing. So if we want to know, or there are two questions you can be asked. Let's say certainty, uncertainty in position. This is uncertainty in position. It means you'll have to rearrange this equation that the minimum uncertainty in position greater or equals to Planck constant over 4 pi. You know the numerical value for pi? Well, 3.14 times mass, which should be in kilogram, times uncertainty in velocity. This is because of the Planck constant. This is Planck's constant. And this is the speed. All right, the speed in meters per second. We need to change that. So this is one of the equations used in Eisenberg uncertainty principle. Uncertainty in position. So if you are asked to calculate uncertainty in position, that's the equation. And then N in velocity, not equals, it is greater than. Let me make sure that I get right. There is greater than. Equal or greater than. This means equal or greater than. equal or greater than Planck's constant over 4 pi over times mass times uncertainty in position x. So this is equation 2. You're gonna need that. So if you are asked to find the uncertainty in velocity, it is greater or equal to the Planck constant divided by 4 times pi times mass times uncertainty in position. Uncertainty in position. They are complementary. This means the more accurate you know the position of a small particle such as an electron, the less you know about the velocity and vice versa. The more you know this one, the other one is compromised. So the two complementary properties of an electron in an atom is its speed or velocity and the position in an electron. This is Heisenberg who came up with the principle. And it's the same equation I just walked you through and how to apply in calculation. This is version A. If you are asked to find the uncertainty in position, you just punch in everything there. And if you are asked to find the uncertainty in velocity, this is what we need to proceed with our calculation. Here is an example on uncertainty principle. This problem is from the text, page 352, number 57. So let's go. An electron has uncertainty in position of 552 picometers. What is the minimum uncertainty in velocity? So this is the equation we're going to be using. All right. This is the equation we'll be using. Uncertainty in velocity is greater or equal to Planck constant over pi times 4 times mass times uncertainty in position. Take note of uncertainty in position. It should be in meters. So expect to recall the Greek prefixes. PM stand for picometers, and 1 meter equals to 1 in the 0 times 10 raised to negative 12 1 meter equals to negative into 12, so into 12 picometers. And 1 picometer equals 1 times 10 raised to negative 12 meters. So a nanometer, meter, picometer times 10 raised to positive 12, 1 picometer. So we will use this to change the mass from picometers to meters. So convert uncertainty in using this equation 552. I want to get it to picometers. I'm looking for meters. So 1 meter 1 times 10 raised to negative, no, this is positive. It's gonna be positive. So that picometer, and picometer will go. Which is 5.52 times 10 raised to negative 12, not 10. This is what we need for our calculation. We have converted the uncertainty in position to meters. Next is mass. This is an electron. Recall mass of an electron 9.11 times 10 raised to negative 31 kg. That is the mass of an electron. From here, we can now find the uncertainty. Therefore, is greater or equals to Planck constant over 4 times pi times mass times uncertainty in position x. 6.626 times 10 raised to negative 34 over 4 times 144. Mass, we have just converted that to kilogram. Ten is negative 31. This is 31 right there. Kg times change in uncertainty in position is 5.8 times 10 raised to negative 10. If you plug in everything, you should get 1.04 times 10 raised to 5. There is the uncertainty in velocity, meters per second. Uncertainty in position, meters per second. Please practice with problem number 52, 53, 54. All right, I've put 53 twice, should be 1, and 55 on B3. 52 from B3, 52. So practice on those on Heisenberg uncertainty. The key thing here is remember the mass of an electron. All right, you have to look at it from the part of the text, or you can yeah, it's given, you'll be given in the quiz if need be. But for homework assignment, you may need to look for masses. You may need to look for conversion. You need to know that always mass has to be in kilogram. You need to change to kilogram. Velocity has to be in meters per second. It's gonna give you that. So that's enough of de Broglie, Heisenberg uncertainty. What about not de Broglie? Heisenberg uncertainty in position and velocity. Remember the complementary properties. The more you know about this, the more you know. And that's why we ended up with this principle. Hence, Heisenberg uncertainty principle to account for or take care of the complementary properties of an electron. Earlier on, at the beginning of part A, I talked about the notion in the beginning, before the 20th century, that matter was deterministic, which means we can determine the outcome. If I drop something, it's gonna fall on the table. We can determine, but experiment by Fergus scientists I planned in part A demonstrated that there was indeterminacy in matter. It changed the whole equation. I talked about that. You can read more in the text, determinacy and indeterminacy. There's some demonstration, illustration on what this means. Turns out that when they probe and look at the atom, electrons are indeterminate, which means you cannot determine where the electron is traveling. Remember, we are talking about the probability of finding an electron. So determines a definite, we can predict the future. I just gave you that if I drop my watch, it's gonna fall down, we can predict that. But when it's come to small particles such as an electron, think about the electron right now, because we cannot know both the position and the velocity of an electron. Remember the position, they are complementary. The more we know this, the more we don't know about that. And in particular, electron here, we cannot predict the path until, but it will follow the next thing. Indeterminacy, indefinite future can predict only with probability, but we cannot tell. The other uses are, some illustration here to show what is meant by probability and what is meant by just classical trajectory. Here, the dots you see here is just any of these dots represent the path of an electron. If it was an electron, it can be anywhere. But here it is predicted that the player will catch. But here the player may not, they may miss, but along the path there is high concentration of high probability of catching the ball if it was an in ball. So remember that in chapter 8.4, do more practice on de Broglie wave equation to find the wavelength of an object, and also read on Heisenberg uncertainty principle and the complementary properties, that is the position and the velocity of an electron. You should be able to calculate either uncertainty in position, uncertainty in velocity. Moving on to 8.5, this is now when we look at the quantum mechanical model of an atom. In part A, I gave you models of the atom. There are four. Bohr's atomic theory, the Bohr's model, which was in theory, he gave out his opinion on what the atom is all about, explaining. And then J.K. Thomson, Plum-Paddy model of an atom, and then Rutherford nuclear model of an atom. And this is where we are right now. The quantum mechanics and the atom, or quantum mechanical model of an atom. Let's first revisit the concept of kinetic energy. If an electron is moving around the nucleus, right? Makes sense that it has kinetic energy. Kinetic energy is the energy in motion, and recall mass has to be in kilogram and velocity has to be in meters per second, so that we can relate the units of energy, which is the joules, with the kilogram times meter square of second square. So for an electron with a given energy, because of the uncertainty, we can only talk about the probability of finding an electron in certain region in an atom. There is high probability of finding an electron in an atom in a certain region or within an atom. So many of the properties of atoms and to greater extent properties of element has to do with the energies of electron in atoms of those elements. So we have an element, and an element is made up of what? Made up of atoms. The behavior of electrons, or rather the properties of an atom, is related to the energies of electron in that. Oh, well, to try to locate the electrons in an atom, there is what we call this Schrödinger equation. Is it Schrödinger equation? Nevertheless, the scope of this equation is beyond this course, but we will just have to limit our understanding, and the depth we will go to the solution of the wave function, which we call the orbital solution of the equation. Solution to this equation is produce many wave function, which we call the orbital. The square of the wave function is called an orbital. All right. An orbital, so that you understand here, orbital, which you need to know, is a region I defined earlier on, region atom with I electron. Region, so you read this as region in an atom with high probability of finding an electron in a region of an atom. Yes, so this is what you do, or how you define the orbital. An orbital is described by what we call quantum numbers. So you can define this. Let's see the same thing. An orbital is described by what we call quantum numbers. All right. And solution to wave function this shows that the size, shape, and orientation in space of an object is determined by three integers, which we need to learn what they are. The quantum numbers. Quantum numbers are n, l, and m. We call it principal quantum number, angular quantum number, angular momentum quantum number, magnetic quantum number. We read m's of L. This is called m's of L. You read this, and then subscript L, m's or m's of L, something like that. M's of L, magnetic quantum number. I know you are familiar with the principal quantum number. It's just if that is, this is the nucleus. So the energy level, 1 energy level, 2, you recall that the closer to the nucleus, 1, and equals to 2, and equals to 3, closer to the nucleus, L equals to 1 as you move away. We are going to look at these quantum numbers one by one, and these quantum numbers are used to describe what we call orbital. Okay. Now, there is the principal quantum number for just an electron. This is the region of space we call orbital. It's just explaining the region of space where there is high probability of finding an electron. The more dense the dots are, the more likely of finding an electron. We call that an orbital. Now, solving the wave equation gives a set of wave function or orbital and their corresponding energies. I want us to look at the wave numbers. Principal quantum number. And what they represent, this is what we call the principal, the main N designated with an N, and it indicates the energy level 1, energy level 2, energy level 3, energy level what? Level 4, and so forth, within an orbital. It detects values 1, so principal quantum number. One, two, three, all the way to N. That is what is meant by here. The values are integers greater than 1. So it can be 1, 2, 3, so forth. So long as it is greater than 1, greater than 1. So energy level 1, energy level 2, energy level 3, and so forth is the principal quantum number. This corresponds to the values in Bohr's model. Remember, Bohr's model looked like this. So Bohr's model. Angular momentum, it is L. Let's see to here. Angular momentum, angular momentum. And it is designated using letter L. This one takes values. It is 0 all the way to N minus 1. It indicates the shape of orbital. It indicates the shape. So L indicates the shape of orbital. And it can be L zero, 1, 2, 3, 4. It will be S, P, D, F, G. Please learn how to reproduce so that if L is 0, and then we're talking about S. If L is 1, and then it's going to be P, D, and F, and so forth. We may not go as far as the G, just learn how to reproduce that. So this one indicates the shape of the orbital. We'll look at later on the spherical, we talk about the dumbbell. Those are the shape of orbital, and it is represented by the angular momentum quantum number. The purpose of angular momentum is to show the shape of orbital, the shape of orbital. The values I just gave you here, take the values 0 all the way to n. What does this mean? If n, let's say n equals to 3, that means L can be 0, it can be 1, and it can be 2. If n, to understand how m's of L are determine 0. So if, and remember I'm saying if, so here if n equals to 5, possible values for L will be 0 all the way to n minus 1, which means n minus 1 is 4, 5 minus 1 is 4. So the values will be 0, 1, 2, 3, and 4. So these are the values for possible values for L if n equals to 5, if n equals to 5. You got to be able to state the number of L, or they are given n. One more, if n equals to 4, possible of L all the way to n minus 1, which is 0, 1, 2, and 3, because n minus 1, which means 4 minus. So these are the possible values for L, for L. So that's how you determine the angular momentum quantum number L. It represents the shape of the orbital. This, you need to know how to write this. This is the letter used. I know you have seen this before, SP. Remember the S sublabel, P sublabel, D sublabel, F sublabel. And it originated from the lines. Remember the line spectrum, there was a red line, there is a green line. This had to define the shape, sharp, diffuse, and so forth. I don't want to get in details into what those stand for, but it originated from the line spectrum. Sharp line, that is why we have S here. This means something, this may mean that, it had to do with those lines. But nevertheless, come back to angular momentum. If L is 0, it means it's S sublabel. If L is equals to 1, that means P sublabel, D sublabel, and so forth. Quantum number is magnetic quantum number designated using M and subscript L. It is M and subscript L. You read this as M of L. M of L is called magnetic quantum number, and it takes the values for M of L is ranges from negative L all the way to positive L. I know it's kind of like hard to understand what negative L, positive L means. You have to have the L first, angular momentum quantum number, before you determine the numerical value for M of L. For example, if L equals to 2, and then M of L is equals to negative 2, negative 1, 0, 1, 2. You see, you start from negative L to positive L. If L equals to 1, and then it's just going to be -1. This is m of L. M of L is -1, 0, +1, -L to +L. That's how to determine the value for m of L. Once you figure it out, the angular momentum, that is the L values for quantum magnetic quantum number, we can the quantum magnetic quantum number describes the three-dimensional orientation of the orbital. Remember what we defined the orbital? So 3-dimension. The values ranges from -L to +L. You see here, it means -L equals or less than to positive. I'll rather meet people with this fashion. It's easy to determine the values for m of L, m of L. There are on any given energy level, they can be up to 1s orbital, 3p, 3d, and so forth for m of L, m of L. We know n principal energy level, the sub-level, all right, sub-level, they may have different orbitals type within the subshell. I want you to look at how this table has been derived and how you can use to determine the either number of orbital possible values for m of L. Remember, this is the principal energy level, shell number 1, shell number 2, shell number 3, and possible values for L start from for n equals to 1. We don't have 0, so it's gonna be 1 minus 1 is 0 for possible values for L in principal quantum number 1, and this is designated as 1s. M of L, so if we know the L take -1 to +1. Number of orbitals, total number of orbitals in the shell. Shell number 1, 2, shell number 2, shell number 3, 9, shell number 4, 16. We will see later on how to determine the number of orbitals, if we look at how the number of orbitals. Look at this. For shell number 1, total number of orbitals. Look at this, total number of orbitals in main energy level is given by n squared. Remember, n is the principal energy. So if you look at shell number 1, 1 square will give us 1. Shell number 2, the maximum. Remember, this is the maximum number of total number of orbitals in the shell. Shell number 1. Shell number 3, 3 square. Shell number 2, shell number 4, so 4 square is 16, and so forth. One point you need to remember too is the total number of electrons in the main shell or within the main shell is equals to n squared. So 2n squared. We'll see later on when we get to electron configuration how the total number of electrons within the main shell can be obtained. But for now, let's learn look at the how to determine the number of orbitals within the main shell, number of sublabels. Number of sublabels is given by 2L plus 1. Number of sublabels here is 2L plus 1. So for shell number 2 is L here is 2L plus 1. We have 3 here. If L is 0, that's going to be 0. We have 1 in there. We have 1 for that. So let's look at the example on quantum number and how question can be asked. Please ignore the first part. I means to capture the question, but let's look at practice exercise 1 on the PowerPoint slide. An orbital has n equals to 4 and m sub L equals to -1. What are the possible values for L? These are the multiple choice A, B, C, D. You need to know what you're doing. So at the outset, for this problem, n equals to 4 and L equals to 0, 1, all the way to n minus 1, which means it's going to be 0, 1, 2, and 3. 2 and 3. And the correct answer is A. Remember, this has nothing, m sub L is -1. So that means maybe m value for L is 1 and m sub L will be -1. At the outset, know if n is equals to 4, the possible values for L is 0 all the way to n minus 1. It cannot go all the way to 4. Please figure out how to find possible values for L if you know the principal energy level. Let's say if our n equals to 5, then possible values for L will be 0 all the way to n minus 1, which is 0, 1, 2, 3, 4. It cannot be 5. Those are the possible values for L. There's a follow-up question here. Practice exercise 2. What is the designation for the subshell with n equals to 5, L equals to 1? B, how many orbitals are in this sublevel? C, indicate the values for m of L for each orbital. All right. So first, A. All right, A, let me just minimize this. You see the whiteboard. So A, we know n equals to 5, and then L, take the values. Remember, this is L, and then these are the letters. You need to learn this so that if you're given 0, 1, 2, 3, you should know the letters which is associated with that. This is S, P, D, F. So here we know the principal energy level is 5. And L equals to 1. So this is 5D sublabel, 5D sublabel. So you figured out that using this recall from the angular momentum quantum number, we have the number and then the letter assigned to that. If L is equals to 1, and then the letter for sublabel is B. Follow-up question for this B, what is the question here? How many orbitals are in this? There are 3 orbitals. The number of orbitals is given by 2L plus 1. So it's going to be 2 times 1 plus 1 equals to 3. There are 3 orbitals. This is the equation for determining the number of orbitals if you know the value for L. So L was 1, 2 times 1 plus and 3 orbitals. Indicate the values of M's of L, all right? M's of L. So if, see, this is how you answer that. If L equals to 1, M's of L will be negative L all the way to positive L, which is negative 1, 0, positive 1. These are the possible values for M's of L, for M's of L. Please practice more on how to determine the M's of L or angular momentum given the magnetic quantum number given the angular momentum. Still on learning check, let's look at the problem question 1, question 2 on this slide. What are the possible values for L if n equals to 4? So if n equals to 4, L is 0 all the way to n minus 1, which is 0, 1, 2, and 3. And 4 minus, which is 4 minus 1 is 3. These are the possible values for what? These are the possible values for L, And when I look at the here is 1, let's see, which one is correct here? What are the possible values for N? So 0, 1, it cannot be this, it cannot be this. So I guess they should have been, I may have missed 2 here. There should be a 2, but it is possible. It's just talking about possible. It cannot be negative 3. We don't have a negative, so we rule out what? We rule out C because of negative. We rule out D. They cannot be more than 5. And it cannot be 4. These are the possible, even though we don't have 2. But yes, 0 is possible, 1 is possible, and 3 is possible. The correct answer is B. And then how many different values of M's of L in 5F? So if I have the letter here, this is question 2 on the PowerPoint slide. If this is L and this is the letter assigned to it, okay, we will have letters 1, 2, no, 0. It should start with 0. We have here 0, 1, 2, 3, 4, S, E, D, F, G. We go to G, but this is how you determine the possible values for M's of L. F has L equals to 3, and M's of L, if L equals to 3, M's of L will be negative L all the way to positive L, which is negative 3, negative 2, negative 1, 0, 1, 2, and 3. These are the possible values for M's of L, and if you count, there are 7 of them. How many? These are the 7. All right, these are the 7 values. 1, 2, 3, 4, 5, 6, 7. Correct answer for this is the 7 values. Conceptual question, this is something you need to just learn, commit to your memory. The dash quantum number define the shape. We looked at it earlier on that principle energy level represent the size and the energy of an electron residing in those principal quantum number L. Define the shape, which is the angular momentum. The angular momentum represents the shape, all right? Angular momentum represents the shape. The principle represents the energy. And this is the principle, all right? Principle, and it represents the energy. This is the energy. But L, this is the shape of the orbital. We will look at the shape of orbital in section 8.6. Now, there are dash orbitals in the third shell, all right? Recall our number, or rather total number of orbitals in the main shell or energy level is given by n squared. So if we have 3, therefore 3 squared equals to 9, That is how you determine the total number of orbitals within the main shell. Underline the word here, main shell. You should know what it is. It is the n value, which I'm squaring, and it is 9. It will work for all other shell numbers. Practice with problem number 59, 61, 63, and 65 in the lab, not in the lab manual, but in the text at the end of the chapter. You have these problems on quantum numbers. This is just a review of quantum numbers and what they represent. We say energy level, and you can determine the energy of the principal quantum number using the given equation. This is a constant, and look at what we have. Units for, or rather SI unit for energy is in joules, negative, because the electrons emit or release energy when they relax to a lower energy level. N is the energy level, which can be 1, 2, 3, and so forth. So we can calculate the energy for an electron within the main in an atom. This is moving away from the nucleus, energy level 1, energy level 2, energy level 3, energy level 4. You don't need to memorize all these numbers for each energy levels. Angular momentum, we look at in section 8.6, what they represent. Angular momentum defines or determine the shape of the orbital. S, they are in spherical in shape, 2 balloons tied together, 4 balloons tied together. For D and F orbitals, mainly there are 8 balloons tied together. 8 balloons tied together. There is a picture in the text which represent these shapes. What are the possible values of M of L, or what values of M of L are possible for L of 2? Is going to be negative L to positive L, so negative 2 all the way to positive 2, which is D, negative 2, negative 1, 0, positive 1, and negative. We just revisiting the quantum number m of L given the angular momentum quantum number. So the correct answer here is D. Yes. You need to remember for that. Lastly, on quantum numbers, this is going to be important in chapter 9, electron configuration. We have what we call spin quantum number, and there are only two possible values. This describes the spinning of electron when they occupy the same orbitals. In chapter 9, we will talk about the electron configuration. And when two electrons occupy same orbital, they have opposite spin. Spinning up, all right, is positive 1/2. So what we mean by that is you may have seen if this is an orbital right here, the spinning of electron. So that is up, it is plus 1/2, or if it is facing down, it is minus 1/2. We call this spin. It is spinning in opposite direction. You'll never see two electrons having this spin. They cannot have same spin. We call this M's of S. M's of maybe subscript S for spinning. This is demonstration of what spinning means. This is spinning in this direction. This is spinning in this direction. And for M's of S, there are only two possible values, plus 1/2 or negative 1/2. The spin of an electron describes its magnetic field, which affects its energy. This will be relevant in chapter 9, will play a role when we write electron configuration for elements. So these are the allowed values, plus 1/2 and positive 1/2. Look at the whiteboard. If it is spinning in that direction, positive 1/2. It's spinning in this direction, negative 1/2. So this orbital described, we have talked about principal quantum number N, L, M's of L, and M's of S, and what they are called. So if N equals to, or the number of sublabels equals to the label number, note the number of sublabel in the main energy equals to label number. What this means is, if you want to know how many sublabels you have within the main energy label, there is only one sublabel in label 1, 2 sublabels in label 2, 3 sublabels, 4 sublabels, 5 sublabels. And you should know what they are, be able to define or determine the M's of L for all those. In summary, the number of sublabels in any label is equal to the N number, the principal quantum number. Make note of that. How to determine the number of sublabels. The number of orbitals in a sublabel, not within the main energy label. I know I gave you N squared. Please remember that. It is different from what we have here. The number of orbitals in any sublabel is given by 2L plus 1. The other one was N squared. Draw the parallel for that, please. Therefore, the sublabel L equals has 1 orbital, which is B. L equals to 1 has 3 orbitals, and so forth. Lastly, the number of orbitals in the main energy level equals to n squared. It's different from here. I know when you say number of orbitals, are you talking about the sub-level, which is 2L plus 1, or are you talking about the main energy level, which is n squared? These are small bullet points you need to understand, commit to your memory, so that you can apply once we get to write the electron configuration, right? The electron configuration of elements. To this point, atomic spectroscopy, which we looked earlier on, is explained here using quantum mechanical model. Atomic spectroscopists explain that each wavelength in spectrum of an atom corresponds to an electron transitioning between quantum mechanical orbitals. Remember, there is energy level 1, energy level 2. So transitioning between main energy level leads to atomic spectroscopy, the atomic spectroscopy, which is the interaction of light with matter. In this case, matter is electrons. Now, when an electron is excited, it transitions from an orbital in lower energy level to orbital in higher energy level. What this means is, if this is an atom, all right, with energy level, you see energy level 1, energy level 2, if this is n equals to 1, n equals to 2, n equals to 3, n equals to 4. If an electron is initially here, this is an electron with negative, and assuming that there is light or particle of light interact with that, this electron will be promoted to this. We call this excited state. And here, the original is called ground what? Ground state. Ground state, so that you know what is meant by an excited. An electron is excited, transition from an orbital in low. It was somewhere here, not necessarily 1, but so long as it can jump from one energy level to a higher energy level, we say that electron is excited. That electron is excited. When it relaxes, it emits light or energy. So if it is relaxing, coming down to where it was, like that, light is given off, or a particle, a photon is given off with a characteristic wavelength. That means relaxing, coming down to where it was. Energy is given off. Let's look at the transition and how to calculate the energy for each line. So if it relaxes, let's say electron was in the energy level 1, interacting with light, jump to energy level 3, and electron absorb light. You see this? This is absorption. It's jumping. So there is a photon here. It's jumping all the way to n is equals to 3 or any other higher energy level. If it comes down, light is emitted as electron fall back to the lower energy level. Energy or light is given off. Light is given off. So we can predict for hydrogen the amount of energy over photon of light given off when electron relaxes. You see, this is energy over photon, energy over photon. So if an electron is relaxing to a lower level, this is a photon of light being given off. And the energy of that photon is a function of the two principal quantum numbers. Where is this starting from? This is energy level where the electron is dropping from, and this is where it is relaxing to. We can find the energy of that using this equation, negative 218 times 10 to negative 18 joules is a constant. You plug it in the equation to get the energy. Probably maybe like solving one example might help in determining the energy level, so that we have that. You can see how to determine the energy of an electron. Remember, this is for hydrogen. An electron in should be 1 in n equals to 7. This is principal energy level 7 of hydrogen atom relaxes to a lower energy level, emitting light of 397 nanometers. What is the value of n for the level to which an electron relax, How are we going to solve this? First, we need to calculate the energy. All right. Using this equation, we know energy of a photon one lambda. At the beginning, or at some point, I gave you this. This is Planck's constant. And the 10 raised to negative 34 joules per second. And c is the speed of light in a vacuum, 8 meters per second. And then the wavelength, we have been given the wavelength, and because the speed of light or the speed of electromagnetic radiation is given in meters per second, we need to change this to meters using the appropriate conversion factor, 397 nanometers. We want to get rid of nanometers, we want to remain with meters. So 1 meter equals 1 times 10 raised to negative 9, not to positive 9. 1 meter equals 1 times 10 to 9 nanometers. If you plug in your equation or in your calculator, this is what you should get. Negative 7. So this is the wavelength. That is the wavelength, which we will apply now in this equation. So we know this, we know this, we know this. So we can calculate the energy. Therefore, energy times 10 raised to negative 34 to 30 seconds over further from here, C over the lambda, which is 397 times 10 raised to negative 7 meters. So that meters and meters will go. And the value for energy here is 5.00 times 10 raised to negative 19 joules. Please confirm with your calculator should be the energy. So we have used the equation to calculate the energy of the photon first so that we can now use this equation. Let me just go back here, show you this equation. So now we know the left side, we can plug in these two values. This is where it is dropping from. This is what we are looking for, where it is relaxing to, negative, negative. The positive, you see positive. So here the E, which is the energy of a photon, times 10 raised to negative 18 goes into 1 over n squared minus 1 over 7 squared. Reason for that is, you see, relaxes to a lower. Remember, this was final or initial. And this is the final where it is relaxing. That's how I know from that equation. From that equation here, this is the initial. It was starting from energy level 7 to some lower energy, which we don't know. So if I plug in the equation, the energy for that, it was 5 on the right side, 5.0 times 10 raised to negative 19 joules equals to 2.18 times 10 raised to negative 18 into 1 over n squared minus 1 over 49. If we divide both sides by 2.18 times 10 raised to negative 18, this will go and this will go. Divide that by 2.18 times 10 raised to negative 18 joules, some joules will go, which means if I flip the equation, one over n squared equals to 0.2293 plus 0.0204. I know you may be wondering where the numbers are coming from. What I did is from here, 1 over 49. This will cancel away. And if I divide that, then you take across the equal sign. I want to remain with 1 over. So 1 over 49, you should get a value, take across the equal sign, you add with the value you get from here. And that's what I'm doing here, which means 1 over n squared equals to 0.205. N squared equals to 1 over 0.25, which means n squared equals to 4, n equals to 2. That's how you find the energy level where it is relaxing to, using the equation for the energy of a photon transitioning from one energy level to another energy level. This is the initial, that is the final. This is a constant which will be given, and this is the energy of a photon. You need to remember that. And that is it for this learning check. Please look at problem number 71, 72, 73, and 75. 77 on page 353. Which transition emits light with the shortest wavelength? Shortest wavelength. All right. Shortest wavelength means the one with the greatest energy. Remember, as you go away from the nucleus, the energy levels keeps on closer and closer, which means the electron will not have higher energy. So the one closer to the nucleus, which is n equals to 3 to n equals to 2, will have the shortest wavelength because it has greater energy, because it cannot greater energy. So he suggests the transition for hydrogen, not a big deal, explaining the 4 colors we saw in the line spectrum. Where is it transitioning from? Okay. Ground state, the lowest energy level, excited when it goes up. This is the ground state, but when electron jump from lower energy level to a higher energy level or where it was, we say that it is excited. So note the excited state and the ground state for an electron. Since each orbital has a specific value compared to rate spark constant, transition from one energy level to can be calculated. This is the energy difference we can calculate, and this is what we used in the previous slide, yeah, to calculate the energy difference. If it's change in energy is positive, it means energy is absorbed. But if it is negative, it is emission. We have emission for positive or negative. The energy in joules required for an electron transitioning in 4 hydrogen atom from n equals to 1 to n equals to 2, how do we determine the amount of energy in joules? Energy in joules. What we need to understand is change in, all right, change in, let me show you my whiteboard, change in energy is given by negative 2.18 times 10 raised to 18, negative 18 joules, 1 over n, f minus 1 over n I. Well, this is final, this is initial, where it is starting. So here, from to, so this is our final, this is our initial. So if we plug in that, this will be negative 2.18 negative 2.18 times 10 raised to negative 18 joules into 1 over 3 squared. This is the final 1 over 1 squared. Remember, from to final. Into negative 0.889. This is positive 1.94 times 10 raised to negative 18 joules. Which is D. The critical point to remember here is the transition and where you started. There was positive, there were negative. Remember in the last section, the transition, if it is positive, it is being absorbed, it's going up. So absorption for positive. Going up, anything greater than 0 is positive. So it's transitioning from a lower energy level to a higher energy level. But if it is negative, and then it's transitioning. It's transitioning. That's the difference for that. Lastly, 8.6. This is the last section in chapter 8, the shapes of atomic orbitals. For s orbital, remember angular momentum describes the shape of the orbital. S orbitals, they are spherical in shape. You may see that the dot density is proportional to the square of the wave function, which is the probability of finding an electron. It does not mean, by the way, I know when you look at the 3-dimension, it does not mean at the center here the electron is closer to the nucleus. The probability density here paint or clearly indicate what is going on here. That as you move away from the nucleus, the probability of finding an electron gets lower and lower, but there is an optimum distance from the nucleus where there is likelihood of finding an electron, probability density. So s orbital, they are spherical in shape. You need to remember that all s, regardless of which energy level, they are spherical in shape. For dumbbell shape, this is for p orbitals. It's just like dumbbell, sometimes dumbbell or 2 balloons, 4 balloons for d orbital, and 8 balloons for f orbitals, 8 balloons for f orbital. So to really understand, instead of using just the dots here to indicate the density of the density of finding an electron, or dot density to indicate the probability of finding an electron, you can draw the probability density as a function of the distance from the nucleus. Here we are just being given for hydrogen. You can do, or you can draw the total probability density for other orbitals as well, 3s and 2b. This does not paint a picture of where the electrons or an electron is likely to be found. But if you look at this, there is an interesting fact here for total radial probability, that the number of nodes equal to the shell number. We have 3. We have 3 for third energy level. We have 2 for second energy level. Well, I want you to read the shapes of s orbital, d orbital, as well as their total probability. You'll be able to draw those as well to really understand. These are the p orbitals. They are like dumbbell, the dumbbell. And sometimes it might be designated using this. You may have seen 2px, 2py, or 2pz. This indicates which orientation is the orbital, like 2px is right here, is lying on x horizontally. Now 2py here is lying on the y-axis, and pz on this lying on the z-axis on the 3-dimension. I'll not ask you, to memorize these, but just only know the shape One last thing I want to mention in section 8.6 is why do orbitals, all right, have spherical? Why do we represent atoms, sorry, atoms as spherical? You may have seen that over and over. The answer for that is because of, look, the answer for that is because all orbitals together makes up a roughly spherical shape. So we have all orbitals in this diagram, and that explains why authors use spheres to what? To indicate atoms. It's just because of all the orbitals, when you combine them, they assume the spherical shape. Assume the spherical shape. That marks the end of chapter 8. I don't want to proceed. This is just a repetition of what we went through. All right. You can read more on the shapes, probability, density, and so forth. But for now, I want to stop here and just wrap up chapter 7, 8. And before we do that, here is a typical question you expect to see in exam or a quiz. Dash orbitals are spherical. These are just the s orbitals. It's easy. S orbitals are spherical. The p orbitals are symmetrical equals. These are the p orbital. P orbital. Let's see the chapter 8. Alex assignment is due not later than August the 3rd. Please make sure you attempt all problems. You can go back to any other module on Alex to improve your grades. Thank you. See you in chapter 9.